Hello, everybody. We are going to broaden our discussion of reactions at a carbonyl carbon to include other groups attached other than the R or the H that makes them a ketone or aldehyde. So that is why this section is called carboxylic acid derivatives. We will interconvert between them and we'll react them and make them, in other words. So let's get started. We are going to first review what makes something part of this carbonyl functional group family. And I know you know all your functional groups by now, but it's kind of nice to just take a pause and revisit what functional groups are we going to be talking about now? Because last section was ketones, aldehydes, ketones, aldehydes, ketones, aldehydes. And they had a very specific mechanism that kind of went along with that. And there's a reason they were separated out. So what makes something a carbonyl containing functional group obviously has a carbonyl. Carbonyl by itself is not a functional group, it's a bond, because it's always part of something bigger that's defined as a functional group. So there's usually that R group here, that, the organic main chain, but then whatever Z is tells us which of the carbonyl containing functional groups it is. So whether it's a carboxylic acid derivative or ketone or aldehyde. So we're going to sort these and remind ourselves what Z could be, at least for this class. So that'll be our variable, if you will. So when Z equals H, it looks like this. And so remember, we have that abbreviation of even this condensed structural formula of CHO. That's an aldehyde, right? That's what we've been doing pretty exhaustively. How about when Z equals R? So if it equals R, then we have an R flanking the carbonyl, which means we have a ketone. If Z equals OH, then on the other side of the carbonyl, we have a carboxylic acid. And so sometimes that's abbreviated RCO2H. And so this carboxylic acid could also be derived from the acid chloride, hence the name acid chloride. So you don't often abbreviate that one as much, just because it's a little less common, but RCOCl would be a way to do that. What if we have OR? So instead of having an OH, we have an OR. That gives us an ester. And that one is commonly abbreviated because we have a whole section with lots more to do with esters. Or RCOOR is another way to do it. How about amide? In order to get to an amide, we have the nitrogen, but nitrogen has more bonds to make. So it can be an NH2, it could be an NH and an R, and it could also be an NR2. So in other words, something that would normally make an amine, but one of the bonds of the amine that would normally be attached to the third H or R is attached to a carbonyl instead. So that R would look like R NH2, NHR, NR2, etc. That gives us an amide. And finally, the bigger one that's a little harder to remember is what if, so it cuts off there, what if we have an ester actually attached there? So when we have our carbonyl and then the other side it's an O joins another carbonyl. This is called an acid anhydride. And there's a reason for that. We're going to actually show this soon, how this reaction forms. But it's because if you take two of your carboxylic acids, and I'm going to write them as mirror images on purpose, just because I think it makes it a little more clear, and we do a reaction where we combine two of them, and we do what's called a condensation, minus water, condensation reaction. So let's take water off. Take an H2 and an O. Notice what's left is an acid anhydride. The two carboxylic acids minus the water, anhydride. So it truly is a carboxylic acid derivative. It was derived from 2 carboxylic acids. So in this section, we will focus most heavily on the remaining groups we haven't talked about yet. So this was the focus of the previous section. And so this chapter will focus on what are reactions of carboxylic acids like: acid chlorides, esters, amides, and acid anhydrides. Why are they covered in this way? Well, we expect the mechanism to be very similar. Notice we have the electrophilic carbon, right? So we still have an electrophilic carbon. We just have different things attached, and that does actually change what happens next. So let's take a look at that, what our mechanisms can be. Okay. So we're going to learn and revisit mechanisms we knew before and how this changes when we have different Z groups attached. So remember, if this was our kind of generic template for our carboxylic acid derivative where Z is the variable, and if you were to draw resonance structures for it, we would have the purely isolated charges to illustrate that dipole nature. So the hybrid would be represented by partial pi bonds where there was one pi bond, but not here, and partial charges where there were sometimes full charges. So the reason we draw the hybrid is because that represents sort of like an average of these contributions, and so that's the more accurate depiction of what the molecule looks like to a neighboring molecule. So in other words, this doesn't have a plus visibly on it, but it has partial plus character. We see that in the hybrid. And so that's why I'm emphasizing that here, because we want to just remember nucleophiles are still attracted to that carbon center because it is still an electrophile whether Z is there or not, no matter what Z is. However, Z can influence the electrophilic character of it. So in other words, let's think about that for a minute. Considering this resonance hybrids, what Z group would make the carbonyl more reactive? Well, the carbonyl serves as it's one of 2 answers, electrophile or nucleophile. The carbonyl carbon serves as I'm going to write it down, see if you match me. Electrophile. How do we make electrophiles more reactive? We make them more positive. So we want that delta plus to be even bigger. How do we make that delta plus bigger? We make Z more electron withdrawing. If it withdraws electrons from the carbon will experience even fewer electron density around that carbon, making it more prone to nucleophilic attack. So in other words, let's summarize that. If you increase the electron withdrawing group ability of Z, that increases the delta plus, which results on the carbon see what happened here, C, and which increases its reactivity. If we decrease the electron withdrawing ability, so how about we call that electron donating effect? So if you increase the electron donating ability of Z, we decrease the delta plus on carbon, so it's not as good of an electrophile. That means a nucleophile will not be as attracted to it. So that will decrease its reactivity. So who can do this? So of the list, of those on the list on the previous page, we're going to include all of them. H, remember H contributes nothing. R is weakly electron donating. O is electron donating, strong. Cl is electron withdrawing. OR, electron donating. And then I would say more or less weakly electron donating, right? So really the only one that's electron withdrawing is chlorine. So in other words, out of everything on there, acid chloride should be the most reactive based on this investigation we're doing right now. Decreased interactivity would come from electron withdrawing groups, so R groups, like a ketone, ester, amide, etc. Okay, so that is part one. How attractive are those intermolecular forces to once you take into account Z is variable? Now another thing to consider. Not all Z's are equal. So in the previous section, R and H were horrible leaving groups, right? So we didn't have it ever leave, but chlorine's a good leaving group. Okay, so what happens if we have a good leaving group? Let's look at our mechanism again, what it can do. So let's say we let Z be leaving group. And then we have a nucleophile, because chlorine's not the only leaving group. Let's write out our mechanism. Attack, we know that one very well. Open. So far so good. Draw the tetrahedral intermediate now. New group and O minus. Remember, we're chiral now too. Okay. If Z is a bad leaving group, then we would do protonate and be done, because it won't leave. That's what we did with ketones and aldehydes, because R and H are not leaving groups. However, if it's a leaving group, why wouldn't it leave? So in other words, instead of protonate, instead of attack, open, protonate, we could do close, because it's actually favorable to reform the carbonyl. That's a strong bond that's favorable thermodynamically. Close, kick. So those are new steps. Close, kick. Now, that's not an official sequence of terms for this mechanism, but I give credit to my organic professor, Betty Lucet, who she's retired now, but she simplified that and said, look at all of the carbonyls with leaving groups attached. They do an attack, open, close, kick. And I thought it was brilliant, because suddenly it was like it all crystallized clear to pattern all of those mechanisms after those 4 steps. So that'll kind of be the theme of this chapter, attack, open, close, kick. And like the last chapter, for the most part, except for some of the unusual mechanisms, we did a lot of attack, open, protonate. So we're going to do attack, open, close, kick. If there's a leaving group. Got to look for that. Those are our 2 main scenarios. So notice we end with a different looking product. When you do attack, open, protonate, you have an alcohol at the end. Now we have a carbonyl containing functional group again. So you can interconvert them. So I'm going to just say keep the carbonyl. It's not alcohol. Okay, so what we essentially did, we should be able to look at a reaction by now. We've learned a lot of categories and fitted into the official label based on what happened. We have the starting material and the final product. If we ask ourselves what changed, well, this part stayed the same. The leaving group left, and the nucleophile replaced it. That's only one thing that could be: substitution. But it's clearly not SN2, the first substitution you ever learned. I bet you didn't know there's going to be so many after that. It's its own family, right? Substitution is SN2 is a subset of substitution. Substitution. Okay, so the name of this one is nucleophilic. Acyl, because acyl is another word for the carbonyl containing compound. Substitution. No fancy abbreviation for this one. It's not too big of a mouthful. Okay, so of those 7 carbonyl functional groups, which ones can we get to have the Z act as a leaving group? Let's make a list. There are going to be some that leave, even though it defies our idea of a good leaving group. But let's start with the ones we know. Clearly good leaving group, no question there. That's going to do the attack open close kick mechanism. This one makes perfect sense too. The acid anhydride, when it kicks off this group that's attached, we get a resonance stabilized ester. So that's actually favorable. But these last two are strong base anions that we normally would not form very easily. So there has to be a good driving force for that to happen, or some other encouragement with the mechanism. So in other words, we can get esters to have their OR leave, carboxylic acids to have their OH leave, amides to have their NH2 leave. It's just not as easy as these. Okay, much more difficult. Okay. Why? Remember that the stability of the leaving group depends and determines the reactivity of those functional groups. So the stability of it once it leaves. So you want the stable anion. It's all back to Kario again. You know, what makes a stable anion? So we're going to rank them. We're not going to take our time doing Kario analysis fully, but we're going to, using our understanding of Kario, which is, you know, how we rank the stability of a conjugate base of an acid, so an anion stability in other words, we can also rank the stability of the anions once they leave. All right, so do that right here before we do this other reaction. So chloride, I'm actually going to draw the whole molecule. Acid chloride is most reactive. And once again, since we're doing rankings, I'm going to make it extra clear. So acid chlorides are clearly the most reactive. Then acid anhydrides. Both are pretty easy to get going. There's a big difference in reactivity from those onto esters, which are about greater than or equal to reactivity of carboxylic acids, which are similar, but you know, we tend to put amides way down at the end here. Okay, so in other words, we should expect to learn a lot of reactions for this guy because it's just reactive. It's easy to get to react, whereas this one's going to be much more stubborn. 1, 2, 3, 4, 5. But there were 7 groups on the first page. Go back to the first page. Who did we miss? The previous section. Ketones, aldehydes. They were not in this list. Why? Because they are not leaving groups. Z is not a leaving group for a ketone or aldehyde. So, in other words, if Z is not a leaving group, that means we have H or R. They are never leaving groups. That'll make it easy for you to remember. Okay? So, just as a reminder, since H and R never leave, if we take ZR and we define Z as not a leaving group, which means it's either an H or R, and then we add our nucleophile, well, hey, this is just the previous section all reviewed. We do attack, open. But it's worth reviewing because it's nice to see it side by side. O minus, and we have our H or R in our new group. And then we have our workup step, water is added. Protonate. So we have AOP. What does our final product look like? The tetrahedral, very likely now chiral, or at least you have to consider that, alcohol. This is starts as a ketone or aldehyde, and we end with an alcohol that has a new group. That came from the attack open protonate mechanism. Looking back here, compare that to the attack open close kick. Attack open, this is where we stop. These are the steps the same. We stop at this tetrahedral intermediate and say, ooh, is that a leaving group? If your answer is yes, you do close kick. So I'm going to write that out, A-O-C-K for attack open close kick. Because you closed and kicked, you get another carbonyl compound back. You don't get alcohol like you do here. Okay, so those are the two possible outcomes when you are attacking the carbonyl carbon. All right. So the rest of those functional groups, i.e., oh, I actually didn't answer the previous question. What type of reaction is it? It's not a substitution because we didn't actually lose a leaving group. So let me write the answer up there. This is an addition reaction. So if we draw the rest of our functional groups, the other two that were not in the set above that do AOCK, the only two that do AOP, we have ketone versus aldehyde. Who is more reactive? Think about that for a minute. Who's more reactive? What determines the reactivity? Well, you have to find out its role. Carbon's an electrophile, so draw in the delta plus. So who has the bigger delta plus? Well, that depends on what's attached. A ketone has an R group on both sides, and so this, in other words, is equivalent. But on the other side, an aldehyde has an H. Since R is electron donating, that diminishes that delta plus. So what I'm going to do is make this, by comparison, just to kind of exaggerate it, make this a bigger delta plus. And that means it's more reactive. Okay? So when we're given a choice, if ketones and aldehydes are present, especially even in the same molecule, and you're given one equivalent of reagent to it, who reacts? Aldehyde. Template. Let's do some real examples, because that's what we need to kind of start to call out any interesting fine points that we need to add in.